What if I told you that in the very center of Rome, there is a building whose dome, according to all the laws of architecture, should not have lasted even 100 years? But has been standing for almost 2,000. Imagine a vault of such dimensions that even modern engineers look at it with disbelief. It has no steel reinforcing rods, no hidden support trusses, no technologies that we consider essential for such structures. And yet it stands as if defying gravity. The Pantheon is not just a temple, but an engineering marvel in which every detail serves a single purpose: to defy the forces of nature. At the very top of the dome is a huge opening 9 meters in diameter, exposed to rain, sun, and wind. Any other structure with such a weakness would collapse under its own weight. But the Romans found a way to make concrete work in a way that concrete is not supposed to work. They changed the composition of the mixture as it rose, turning heavy stone into a material of almost airy lightness. Watch the video to the end and you'll learn how Roman engineers modified the concrete layer by layer, why the hole at the top makes the dome stronger rather than weaker, and how the hidden geometry of the Pantheon created a structure that has withstood the test of time so well that modern architects still cannot recreate it with the same durability. I will reveal the Pantheon's best-kept secret, which was not in its materials, but in its very concept. When you enter, you instantly feel harmony, but you don't immediately understand why this feeling arises so naturally and rapidly. The impression is not created by the decorations or the grandeur of the columns, but by the very shape of the space, which affects people more deeply than they realize. The architects of Rome sought to create a structure in which each element obeyed strict laws, linking form, light, and scale. The interior space is subject to ideal geometry, which uses human perception as a tool of influence. This hidden design becomes clear only to those who know the mathematical logic of the Pantheon. The secret lies in the ideal proportions, which were not simply an aesthetic choice, but a fundamental engineering calculation. Roman architects consciously sought a form in which there would be no superfluous elements to disturb the balance. The interior volume of the temple is designed in such a way that the space feels both enormous and surprisingly unified. These proportions, calibrated to fractions of a Roman foot, sought to fit humans into the mathematical order of the world. Therefore, the impression of harmony arises instantly, even before the eye has time to study the details. The sphere became the basis capable of combining meaning, symbolism, and precise calculation. Roman architects, probably under the guidance of Emperor Hadrian himself, designed the space as an ideal sphere. The diameter of the dome, equal to 43 3/10 meters, coincides with the height from the floor to the Oculus, creating spatial symmetry. This proportion is not only visual, but also the structural basis of the entire structure. This coincidence of dimensions creates the impression that the dome does not press down from above, but rather seems to grow out of the ground itself. The architects used this equality to connect the heavenly and earthly components of the building into a single system. The interior space becomes an ideal shell in which a person seems to be at the center of a geometric world. This means that an imaginary sphere of ideal diameter could completely fill the interior, touching both the walls and the center of the floor. This illusory sphere transforms the space of the Pantheon into something more than just a room. It becomes a model of the universe. The Romans perceived the celestial sphere as a symbol of divine order, and the architecture of the temple reflects this idea with mathematical precision. Thus, engineering is combined with philosophy to create a building that speaks the language of geometry. The sphere becomes not only an element of architecture, but also part of the Roman worldview. The Pantheon is transformed into a stone embodiment of their understanding of the structure of the universe. This geometry was deeply symbolic and at the same time strictly functional. For engineers, it served as the basis for the distribution of weight and forces throughout the structure. For the Romans, the sphere symbolized perfection, having no beginning and no end. Inside the Pantheon, a person felt as if they were under the sky, separated from the world only by the thickness of concrete. This architectural solution was both bold and poetic. It combined beauty and calculation into an amazing harmony, which created its immortal glory. But for engineers, this shape was a starting point of enormous complexity. Creating a perfect hemisphere out of 5,000 tons of concrete meant fighting the laws of physics. Any error in calculation threatened immediate collapse, because the dome pressed not only on the walls from above, but also from the sides. The structure had to function as a single shell, where each particle of mass supported another. The enormity of the task forced Roman craftsmen to seek solutions that were unprecedented in their era. The sphere required absolute precision and a complete understanding of how the material behaved. Creating such a shape required forward-thinking engineering courage, as building with heavy concrete increased the risk. The Romans understood that the dome would exert pressure around its entire circumference, and the slightest weakness could destroy the building. The reinforcement of the structure began with the foundation, which had to withstand the entire load without the slightest shift. They used mixtures of different densities and thicknesses to gradually reduce the mass of the structure as it rose. This understanding of load distribution was incredibly advanced for its time. The craftsmen created not just a roof, but a complex engineering shell capable of lasting for centuries. This design meant that the walls had to withstand enormous pressure that tended to push them apart. The dome worked like a heavy chain sagging between supports, but inverted and placed in a single space. The lateral pressure was so strong that ordinary walls simply could not withstand such stress. Therefore, Roman engineers made the walls of the rotunda up to 6 meters thick at the base. These massive walls served as a strong frame, keeping the dome in perfect shape. Such thickness was not a luxury, but a necessity dictated by the very physics of the structure. However, this same massiveness created a new problem: the enormous weight of the structure. The thicker the walls, the greater the pressure on the foundation and lower levels of masonry. Engineers had to find a balance between strength and acceptable weight so that the building would not collapse under its own weight. They used lighter materials as they rose, gradually lightening the structure. This method made it possible to significantly reduce the mass of the dome without losing its strength. The Romans seemed to lose weight on the concrete, creating different compositions for different parts of the building. The entire structure was a mathematical puzzle, where each element depended on all the others. The geometric purity of the sphere dictated the need to think through the structure from top to bottom. Engineers understood that using the same concrete throughout the entire height would create uneven pressure and lead to deformation. Therefore, they began experimenting with different mixtures, achieving a gradual reduction in weight as the structure rose. This solution became one of the most revolutionary in the history of construction. No one before the Romans had created concrete with such variable density. They developed a system in which the concrete on the lower levels was heavy and strong, while the upper levels were light, filled with pumice and other porous materials. This ensured a harmonious distribution of load and reduced the risk of collapse. Thanks to this approach, the dome became not a monolithic heavy block, but a multi-level structure that obeys the strict logic of weight. Each part of the dome was selected according to its density so as not to overload the structure. These engineering ideas were centuries ahead of their time. Today we call this a gradient structure, but the Romans achieved it intuitively and ingeniously. The exterior of the Pantheon was also part of the design, concealing the sphere until the moment of entry. The rectangular portico with columns creates the illusion of a traditional temple, which does not reveal the grandeur of the rotunda hidden behind it. This contrast between the exterior and the interior was carefully thought out and created a dramatic effect. One expects to see an ordinary space, but instead finds oneself in a huge light-filled hall. This contrast enhanced the emotional impact, making a visit to the Pantheon almost mystical. The Romans knew how to control the viewer's perception, using architecture as a tool. The transition from the narrow vestibule to the boundless spherical space was part of the architectural drama. It is precisely because of this contrast that the interior space seems even more spacious and bright. One feels oneself at the center of a gigantic geometric structure, full of air and light. The dome suddenly opens up before one's eyes, like a sky created by the hands of masters. This combination of contrast and surprise emphasized the grandeur of the engineering design. The architects of the Pantheon sought to surprise, and they succeeded. The perfect sphere was not just a beautiful concept. It served as a working drawing. It allowed the load to be distributed across the entire surface, turning the dome into a single monolithic shell. The structure functioned as a closed system in which each point supported its neighbors. The engineers understood that only perfect geometry would allow such a mass to be held up. Therefore, all elements, from the base to the top, obeyed a single mathematical principle. Inside the Pantheon, we see the formula embodied in stone. This concept gave the building incredible stability, allowing it to survive earthquakes and the passage of time. As long as the shape remained perfect, the structure remained strong. This connection between beauty and utility became one of the greatest achievements of Roman engineering. The Pantheon survived not by miracle, but by precise calculation. Its longevity is proof of the power of the mathematical approach. The Romans built buildings that were subject to logic, not just aesthetics. We are very interested in hearing your point of view. What do you think about this idea of ideal spherical architecture? Where form dictates structure? Write about it in the comments, and be sure to subscribe to our channel so you don't miss new investigations into the greatest engineering mysteries of the past. Are you ready to learn the truth about the main building material of Rome, which made the Pantheon possible? This material is called opus cementitium, or Roman concrete, and in many ways it surpasses even modern compositions. Unlike modern Portland cement, which is simply a binder, Roman concrete was a full-fledged composite material. Its strength and durability were due to one unique volcanic ingredient. This secret ingredient was pozzolan, volcanic ash that the Romans extracted in large quantities in the Pozzuoli area near Naples. They discovered that when this ash was mixed with lime and water, it formed an incredibly strong and, most importantly, water-resistant mortar. This mixture did not simply dry out, but underwent a slow chemical reaction, forming new mineral compounds. As a result of this reaction, strong crystalline structures formed inside the concrete, which over time made the material even stronger. Roman concrete was not afraid of water. Moreover, it could harden directly underwater. That is why Roman ports, aqueducts, and bridges built using pozzolan have stood for millennia, withstanding erosion and seismic activity. To build the Pantheon, the Romans created a mortar from lime, pozzolan, and water. They then mixed this mortar with aggregate, various types of stones and broken bricks. The laying technology was layer by layer. Workers laid a layer of mortar and then immersed large pieces of stone into it, carefully tamping them down. This method did not create a homogeneous mass, as in modern concrete, but a complex structure where the mortar acted as an adhesive, binding the stone aggregate. The stones bore the main load, and the mortar ensured the monolithic nature of the entire structure. It was an ingenious solution that saved on binding agents and allowed the use of local building materials. The strength of Roman concrete was also linked to its ability to self-repair. Modern research shows that lime particles that did not fully react dissolved over time with water seeping into microcracks. This lime-saturated water then reacted with pozzolan, forming new crystals and effectively healing the crack from the inside. This feature gave the structure remarkable resistance to stress and time. Where modern concrete degrades and cracks over time, Roman concrete only became stronger. It was the ideal material for creating a giant monolithic dome that had to support its own weight without any internal reinforcement. Without pozzolan, the Pantheon project would have been unthinkable. Ordinary lime mortar would not have been able to provide the necessary strength and durability. It was this volcanic additive that gave Roman engineers the confidence that their grandiose structure would not crumble to dust in a few decades. They perfected the technology of concrete production. Different recipes were used for different parts of the building. In the foundation and walls, where maximum strength was required, the concrete was dense and heavy. But as they moved upward, the engineers faced a new, even more difficult challenge. But concrete alone, even such magical concrete, could not prevent the giant dome from collapsing. The Romans used an ingenious trick with weight that still amazes engineers today. Read on to the next chapter to find out how they made the stone almost float in the air. What I am about to show you was a real revolution in construction that was forgotten for 1,000 years. It is the main engineering secret of the Pantheon that allowed the dome to stand. The Romans realized that they could not use the same heavy concrete for the entire structure. The solution was ingenious. They changed the composition of the concrete as the dome was being built, making it lighter and lighter. This process is called the use of graded aggregates. The entire dome structure is divided into several horizontal layers, and each layer used its own special type of stone as a filler for the concrete. The engineers literally controlled the weight of the structure, reducing it with every meter of height. This was an unprecedented technology for its time. At the base of the dome, where it rests on massive walls, the Romans used the heaviest and most durable aggregate. The concrete here consisted of large pieces of basalt and hard travertine. These dense rocks provided maximum strength and stability in the area where the dome experienced the greatest compressive and tensile loads. As they moved upward, about 1/3 of the way up, the composition changed. The engineers switched to a lighter material. Instead of basalt, they began to use tough, compressed volcanic ash and broken brick. These materials were significantly lighter than travertine, but still strong enough to support the weight of the upper layers. This transition was smooth but carefully calculated. The use of brick chips was also a clever move. Bricks, being porous, not only reduced weight but also bonded better with mortar, creating a strong and uniform mass. The Romans did not throw away construction waste but turned it into a high-tech component. The real miracle begins at the top of the dome. For the last highest ring surrounding the Oculus, the Romans used an incredibly light material. They brought it from Mount Vesuvius. It was pumice, a porous volcanic rock so light that some pieces can float in water. The use of pumice as a filler radically reduced the weight of the most critical point of the dome. The top, which in a conventional design would be the heaviest and most unstable, became the lightest in the Pantheon. Pumice-based concrete weighed almost half as much as the concrete at the base of the dome. This strategy reduced the total weight of the dome by thousands of tons. Roman engineers accurately calculated where density could be sacrificed for lightness without compromising strength. They literally sculpted the structure based on the physical loads at each specific point. This approach was a real engineering breakthrough. It demonstrates the Romans' profound understanding of the properties of materials and the laws of mechanics. They did not simply build on intuition, but applied precise scientific calculations. This technology of graded aggregates was lost after the fall of Rome and only rediscovered in the modern era. The Pantheon stands not in spite of its weight, but because of how that weight was carefully distributed. The light top presses down on the stronger middle, which in turn transfers the load to the massive and heavy base. It is a perfect balance of forces inherent in the very material of the structure. If you like how we reveal ancient engineering secrets, please like this video. It really helps us create new content. And be sure to subscribe to our channel so you don't miss new videos about the history of ancient Rome and its incredible achievements. Guess what was the first and main problem in building a dome weighing 5,000 tons? It wasn't the dome itself, but what it stood on. Roman engineers faced two fundamental forces, vertical and horizontal. The vertical force is the pure weight of the dome pressing down. The horizontal force, or spread, is the force with which the dome tends to push the walls apart, like a hoop. To combat these forces, the Romans built not just walls, but a true engineering masterpiece, the rotunda. This cylindrical base has a diameter of more than 43 meters, and its walls are up to 6 meters thick. This incredible mass was necessary to counteract the lateral thrust with its weight. The walls of the rotunda are also built of Roman concrete, but there are some tricks here as well. They are not a monolithic block of a single material. Outside and inside, the walls are faced with strong-fired bricks, which the Romans called opus latericium. This brickwork served not only as decoration, but also as a kind of permanent formwork for the concrete. Workers first erected 2 brick walls at a short distance from each other. Then the space between them was filled with a concrete mixture with large stone aggregate. The bricks protected the concrete during setting and created a strong outer shell that was highly resistant to compression and weather conditions. This technology allowed for fast and very strong construction. The brick layers gave the structure additional structural integrity. The entire wall functioned as a single composite material, with the concrete providing mass and compressive strength, and the brick providing shape and external protection. The foundation under this gigantic wall was also not easy. It goes 4.5 meters deep and is more than 7 meters wide. This foundation is a solid concrete ring that evenly distributes the weight of the entire rotunda on the complex soil of the field of Mars. The engineers understood that such a colossal mass could not simply be placed on the ground. They created a foundation that was wider than the wall itself, providing maximum support area. This prevented uneven settlement of the building, which could have led to cracks and destruction. The walls are not the same thickness throughout their height. They are at their thickest at the base, 6 meters, but taper slightly as they approach the dome. This is another example of how the Romans saved material and reduced weight where possible without compromising strength. It is this massive, heavy, and deeply laid rotunda that is the anchor that holds the dome in place. It absorbs the lateral thrust, preventing the dome from spreading apart. The dome and walls work in perfect tandem, with one part of the structure balancing the other. But thickness alone was not enough to safely distribute this enormous load. There is another secret hidden in the walls, invisible to the eye. In the next chapter, you will learn about the invisible skeleton hidden inside these walls. If the 6-meter walls of the Pantheon were just a solid mass of concrete, they might not have been able to withstand earthquakes and centuries of stress. Roman engineers hid a real power frame made of brick inside this thickness. This system of invisible arches and buttresses is one of the main reasons for the building's durability. It distributes the weight of the dome in the same way that a skeleton distributes weight in the human body. The main vertical load from the dome is borne by 8 giant supports, or pylons, evenly distributed around the perimeter of the rotunda. These supports are hidden within the thickness of the wall. Between them, the wall space is made lighter. We see this from the inside in the form of 8 large niches, which create a feeling of open space. But how to transfer the weight from the dome to these 8 points, passing it over the empty niches? To do this, the Romans used a system of unloading arches. Directly above each niche, deep in the concrete mass, huge semicircular arches made of strong brick are laid. These arches are not visible from the outside or the inside, but they perform a very important function. Each arch collects the weight pressing down from above, and like a bridge, redirects it to the sides, precisely to the tops of the massive pylons. This avoids concentrating the load above the empty space of the niche, which would not be able to withstand it. This technology allowed the architects to create a spacious and airy interior without sacrificing structural integrity. But that's not all. The engineers created a whole multi-level system of such arches. They run one above the other, becoming smaller as they approach the top of the wall. This brick grid permeates the entire structure, tying it together and directing the flow of forces along pre-calculated routes. This brick reinforcement also helped during the construction phase. It served as a frame that gave shape to the concrete mass and allowed construction to proceed in stages. The brick arches could bear the load even before the concrete had fully gained its strength. In addition, the use of different materials, concrete and brick, was a brilliant move to combat thermal expansion and minor deformations. Brick and concrete react differently to changes, and their combination made the wall more flexible and resistant to cracking. This invisible skeleton is a triumph of Roman engineering. It shows that the builders of the Pantheon thought not only about visible beauty, but also about the hidden forces acting within the structure. They created a complex system that actively manages loads. Thanks to this system, the weight of the dome does not simply press down on the walls, but is cleverly spread across them. The load is collected by the arches, concentrated in powerful pylons, and then safely transferred to the deep ring foundation. It was a comprehensive approach to weight distribution. Therefore, when we look at the niches and alcoves inside the Pantheon, we must understand that these are not just decorative elements. They are visible manifestations of a hidden power structure. The voids are as important as the mass because they exist thanks to an ingenious system of unloading arches hidden in the concrete. What if I told you that the smooth, perfect dome you see from inside the Pantheon looks completely different from the outside? This is another clever trick by Roman engineers, directly related to the struggle against lateral thrust. From the outside, the dome is not a perfect hemisphere. Its lower part, or heel, is reinforced by a series of massive steps. These 7 concentric rings, or steps, that we see at the base of the dome are not decorative. They are a structural element that serves as an external counterforce, or ballast. They add enormous weight precisely where the dome is most likely to spread sideways. This extra weight, added from the outside, presses down vertically on the lower part of the dome. This pressure helps to counteract the horizontal thrust force. Simply put, the Romans used gravity against itself. They made the base of the dome so heavy that it simply cannot move sideways. The thickness of the dome is also not constant. At the base, or where it rests on the walls, it reaches more than 6 meters. But as it rises toward the top, the dome becomes thinner and thinner. In the area of the Oculus, the central opening, its thickness is only about 1 2/10 of a meter. This gradual thinning, combined with the use of increasingly lighter materials, was a key strategy for reducing weight. Engineers removed every ounce of material that was not needed. They left mass only where it served a structural function. This variable thickness also helps the dome function as a single arch. The entire structure is in a state of compression. Each stone, each piece of concrete presses on its neighbors, and this compressive force, traveling in a circle, prevents the dome from collapsing inward. Thus, the appearance of the dome was entirely dictated by engineering necessity. The steps at the base are needed for weight and to counteract thrust, and the steeper and thinner rise to the top is to lighten the overall mass of the structure. It is the perfect compromise between form and function. The Romans did not try to make the dome beautiful on the outside in our modern understanding. Initially, it was covered with gilded bronze tiles, which hid its stepped shape. For them, its internal workings were more important than its external silhouette. The Romans added weight on the outside, but ingeniously removed it from the inside, directly from the thickness of the dome itself. In the next chapter, we will finally look up at the famous ceiling and see how they did it. When we look at the inner surface of the dome, we see 5 rows of deep rectangular recesses. These elements are called caissons, and they are another example of a brilliant combination of aesthetics and engineering. At first glance, they seem like mere decoration, but their main function is structural. Each caisson is a piece of concrete that has been removed. There are a total of 28 caissons in each of the 5 rows in the dome. These recesses significantly reduce the mass of the dome without compromising its overall strength. They remove concrete from areas where it does not contribute to the main load-bearing capacity. It is as if material had been removed from the center of a beam, leaving only the top and bottom flanges. According to engineers' calculations, the caisson system reduced the weight of the dome by hundreds of tons. This was critically important, especially in the middle and upper parts of the vault. The lighter the dome was, the less load it transferred to the massive walls and foundation. But caissons are not just holes in the concrete. They are themselves a complex structural grid. The caisson framing creates a system of intersecting ribs that acts as a power frame permeating the entire inner surface of the dome. This grid gives the vault additional rigidity and helps to distribute loads evenly. Note that the caissons are also stepped. They have several ledges that go deep into the dome. This is not just for beauty. This shape was technologically easier to manufacture using wooden templates. In addition, the stepped shape helps to better diffuse the light coming from the Oculus, creating softer lighting. Originally, each caisson was decorated. Historians believe that there was a gilded bronze rosette in the center of each recess. This created an incredible effect of a shimmering golden sky when a ray of sunlight passed through the dome. Unfortunately, these decorations were lost in the Middle Ages. The choice of the number of caissons, 28 in each row, is also a matter of debate. 28 is a so-called perfect number. The sum of its divisors is equal to the number itself. Perhaps this had some mathematical or symbolic meaning related to the harmony of the cosmos. The creation of these caissons was an incredibly difficult task. They were cast simultaneously with the entire dome. This required the creation of a complex wooden formwork that precisely replicated the entire relief surface. After the concrete had set, this giant wooden form was dismantled from the inside. Thus, caissons are a perfect example of multitasking in Roman engineering. They simultaneously lighten the structure, reinforce it with a ribbed structure, solve aesthetic problems, and even improve the acoustics inside the room. They are not just decoration, but a vital part of the structure. At the very top of the Pantheon is its most famous and mysterious feature, the Oculus, or eye. It is a perfectly round opening, with a diameter of almost 9 meters, open to the sky. Many find it paradoxical that engineers left a huge hole in the key point of the dome, its keystone. But this is where their genius lies. The Oculus is not a problem, it is a solution. From a structural point of view, the most vulnerable point of any arch or dome is its apex or keyhole. This is where all the compressive forces converge, and it is here that the material experiences the greatest stress. If the Romans had simply brought the dome to a single point, that point would have been incredibly heavy and would have concentrated a colossal load. By removing the entire central part, the engineers completely eliminated this problem. They replaced the material keystone with a void. Instead, they turned the Oculus ring itself into a giant compression ring. All the forces going up the dome now converge on this ring and compress it. This ring, made of the strongest concrete and reinforced with brickwork, acts as a giant hoop that pulls the entire structure together. It prevents the dome from collapsing inward or spreading apart. Thus, the hole in the ceiling is, paradoxically, the main element ensuring its stability. Of course, the Oculus has other functions as well. It is the only source of light in the building. During the day, as the sun moves across the sky, a bright beam of light slowly travels through the interior of the Pantheon. It glides along the walls, illuminating the niches with statues and the coffered ceiling, turning the building into a giant sundial. This lighting effect also has a deep symbolic meaning. It connects the interior of the temple with the heavens, with the cosmos. The beam of light makes the divine presence almost tangible. It was a powerful architectural and religious statement. But what happens when it rains? Every visitor asks this question. Water and snow fall freely inside. Roman engineers had anticipated this. The floor of the rotunda is not perfectly flat. It has a slight slope from the edges to the center. 22 small drainage holes are located in the very center and at several other points on the floor. They are discreetly integrated into the pattern of the marble slabs. These holes lead to a complex system of underground channels that effectively drain all rainwater away from the building. The system has been working flawlessly for 2,000 years. Thus, the Oculus is neither a compromise nor a mistake. It is a multi-level engineering and philosophical solution. It takes the load off the top of the dome, turns it into a strong compression ring, provides lighting for the entire gigantic space, and creates a unique connection between the building and the outside world. We have examined in detail why the dome of the Pantheon stands, but an equally important question is how it was built in the first place. Creating a monolithic concrete structure weighing 5,000 tons at a height of 43 meters was a task that seemed impossible even for the Romans. The dome could not be erected without a preliminary structure capable of temporarily supporting its entire weight. Therefore, engineers were faced with the need to create a support that would simultaneously serve as a formwork and scaffolding. This support had to accurately reproduce the entire geometry of the future dome. This is where the story of another engineering marvel that disappeared without a trace begins. How could such a huge monolith be cast if the finished form had to hold it until it was completely set? The answer lies in the giant internal formwork, which was not just an auxiliary structure, but the heart of the entire construction process. It served as a temporary skeleton, without which the dome would have been impossible. This wooden structure had to be so precise that any skew could have led to collapse. Given the scale of the dome, its creation required a huge amount of wood and extremely complex labor organization. Such a structure was a real engineering challenge. To create the shape of the dome, the Romans had to build a unique wooden system inside the rotunda. These were not ordinary scaffolding, but an architectural replica of the future dome, which took on the entire weight of the unhardened concrete. The scaffolding had to accurately reproduce the spherical curve of the inner vault, because the concrete took the shape that the formwork dictated. When erecting such a shape, even a few centimeters of error could lead to uneven stress distribution. Therefore, the work of carpenters and engineers was as important as that of masons. Their precision determined the fate of the entire structure. This system, called a hoop or formwork, had to be incredibly strong. It held not only the weight of the concrete, but also the weight of the people who were constantly moving around the scaffolding, pouring new layers. The wooden frame was made of massive beams connected in such a way as to withstand multi-directional loads. Engineers calculated it so that the pressure was evenly distributed across many points of support. Without such strength, the dome could have destroyed the entire structure during the construction phase. It was the reliability of this formwork that ensured the further success of the project. Historians still argue about the exact appearance of this structure. Some believe that the scaffolding completely filled the entire space of the rotunda, turning its interior into a wooden labyrinth. Others argue that the Romans used a more rational system consisting of radial and transverse beams that evenly supported the spherical shape. Both options require tremendous skill because we are not just talking about scaffolding, but a complex engineering structure. There are versions that in the center there was a temporary tower that supported the highest parts of the future vault. Whatever the exact option was, one thing is clear. It was a construction project that could only be carried out by engineers of an exceptional level. Most likely, the formwork was a system of beams arranged according to the ribs of the future sphere. These beams could rest on the walls of the rotunda and also be connected to each other through a network of horizontal decks. This system allowed workers to move across the entire surface of the dome, effectively standing on a giant wooden shell. As construction progressed, the scaffolding was gradually extended, following the contours of the vault. Each element had to be fitted precisely, because deviations in geometry would have disrupted the symmetry of the dome. Building such a structure was no less difficult than creating the concrete itself. This formwork carried enormous loads. It supported fresh concrete, tiles, stones, cradles for materials, and platforms for workers. Every day, hundreds of people were on it, moving mortar, tools, and building materials. The structure had to withstand constant vibrations and accidental shocks, which were inevitable with such activity. A mistake in the design could have led to its collapse and, with it, the death of hundreds of builders. Therefore, the formwork was checked repeatedly to ensure that each beam was installed correctly. It was the foundation of the entire construction logistics. The wooden formwork had to be perfectly calibrated. The dome of the Pantheon has precise geometry, and the slightest deviation could disrupt the load distribution in the finished concrete shell. The engineers knew that the concrete would only work as a single structure if the formwork was perfect. Every curve, every line had to match the calculations. If the scaffolding had been built asymmetrically, the concrete would have set with micro defects, leading to stresses. Therefore, the accuracy of the layout and installation was critical. It was an example of mathematics being transformed into matter. Construction proceeded in horizontal layers, ring by ring. Workers poured one layer, waited for it to set, and moved on to the next. The concrete gradually rose, forming a dome as if it were growing from within. Each new layer required a new level of decking and a new line of formwork. The process was slow but extremely reliable, allowing the huge shell to be formed gradually. This method of construction required a high level of organization and precise timing. This process required the perfectly coordinated actions of hundreds of workers. Each layer of concrete had its own composition, and the builders knew exactly which filler to use to reduce the weight of the structure. Heavier mixtures were used for the lower layers, and light porous materials for the upper layers. Each ring of the dome was a kind of experiment that required constant monitoring. A mistake could mean having to dismantle a section and start over. Therefore, the construction crews worked under the strict supervision of experienced craftsmen. Any great building begins not with the roof, but with the foundation. The Pantheon stands on the former Campus Martius, which in ancient times was a marshy, low-lying plain. Building such a massive structure on weak ground was one of the most difficult tasks for Roman engineers. A mistake in the foundation would have rendered all other innovations meaningless. To ensure stability, the engineers decided not to build separate foundations for each part of the building. Instead, they created a single, massive ring foundation under the entire rotunda. This foundation is a giant concrete ring, 4.5 meters thick and more than 7 meters wide. This ring foundation was cast from the strongest and heaviest travertine-based concrete. It goes deep into the ground, distributing the enormous weight of the rotunda and dome over the largest possible area. This solution, similar to the principle of snowshoes, prevented the building from sinking into the soft ground. The creation of such a foundation was a huge construction project in itself. Workers had to dig a giant ring-shaped pit, constantly battling groundwater. They probably used wooden sheet pile walls and drainage systems to dry out the worksite before pouring the concrete. The single ring foundation solved another important problem, the problem of uneven settlement. If different parts of the building had separate foundations, they could settle into the ground at different rates over time. This would lead to cracks in the walls and the destruction of the dome. The ring foundation forced the entire building to settle as a single unit. This uniform settlement did not cause critical stresses in the structure. The genius of this solution is that it ensured the stability of the Pantheon for 2,000 years, allowing it to survive numerous earthquakes that destroyed many other Roman buildings. We can see that the dome of the Pantheon is not just a miracle or a lucky coincidence. It is the result of cold calculation and a series of ingenious engineering innovations. From perfect spherical geometry and magical pozzolan concrete to invisible unloading arches in the walls, Roman engineers solved a seemingly impossible task. They did not simply cover a space with a diameter of 43 meters, but did so with an elegance that still inspires admiration today. They made the 5,000-ton dome support itself, perfectly balancing the weight and distributing the load. What other engineering marvels of antiquity would you like us to explore in future videos? Perhaps you are interested in aqueducts, the Colosseum, or complex siege engines. Suggest your topics in the comments. And don't forget to subscribe to our channel so you don't miss out on new research into the great structures of the past.